Gary Brown, Mechanical Engineering here with another engineering mechanics video. This time we're going to look at the vector formulation of a moment of a force. So let me share my screen and we'll get into it. Okay, so you should have access to the PDF notes via Canvas. So if you haven't got those, you can get those. All right, so let's work our way through the PowerPoint slides. So the lecture objectives to understand and define what a moment is. So you should have already done that to some extent when we looked at the scalar formulation. To determine the moment of a force in 3D, revise cross product, which we'll need to do in order to do the 3D or the vector formulation of the moment of a force, and we'll use that vector cross product in some examples. So the moment of a force is, as we've discussed before, the tendency to cause rotation of a body about an axis, some distance from the line of action of that force. Okay, so we've got some arbitrary shape here, arbitrary body, a rotation axis and a force applied to it over here, acting upwards to the right in the picture, and that would tend to cause a rotation about some axis. Okay, so fairly intuitive, straightforward. In vector calculations or vector algebra, we use the vector cross product to determine the magnitude of the moment and the direction of the moment. Whereas when we looked at scalar formulation, we just looked at the magnitude, pretty much just did force times distance, and the direction of the moment vector we didn't really talk about. So the formulation or the equation for a moment in vector form is R cross F, where R is what we call a position vector to the line of action of the force. Okay, so we have force, which we know is a vector, and then the position vector, which we use to calculate the moment, is the vector from the point we want to calculate moments about to any point along the line of action of the force. Okay, which I've just put there in the dot points in the PowerPoint. So next page, I've just repeated that there. A moment is a vector with magnitude and direction. So previously in the scalar formulation, we just looked at the rotational effect and calculated its moment, its magnitude as force times distance. But a moment is a vector with magnitude and direction just the same as a force is. And the way we determine the direction of the vector moment is to use the right-hand rule. Okay, so here we've got the right-hand rule. Our fingers rotate in the direction of rotation and our thumb points in the direction of the vector, or points in the vector direction. So if the force vector is in the XY plane and also the position vector, then the moment vector is in the Z direction. Okay, so when we looked at scalar problems before, and most of them that we looked at were in X and Y direction, the moment was actually in the Z direction, either into or out of the page. Okay, so perpendicular to the plane in which the position vector and the force vector are placed. Okay, so I've just shown that here with some coordinate systems. The vector equation must be R cross F. We can't do F cross R because we'll get the moment direction in the wrong sense. So we'll see that in the cross product revision in later slides. Okay, so this is just a bit of a summary of just what we said. So we've got a force vector, a position vector, defining its distance or location from some point O that a moment axis passes through. And the moment about point O is R cross F, which I've again showed here. But if we look at what we've got here, we can see if we draw a right angle triangle here and we draw this line here perpendicular to the line of action of the force, right, and we call this dimension here D, we can see that D will be R sine theta. So we can calculate the moment about point O by using the magnitude of the force times the magnitude of the position vector times sine theta, where theta is the angle between the position vector and the force vector. Okay, so again, just rearranging that and expanding it, we can see here also if we take consider components of the force. So we looked at previously the scalar formulation and we looked at Varanon's theorem, or the principle of moments. If we break this force up into its components along the direction of the position vector and perpendicular to that, we'll have F sine theta, right, will be the component here, and then the component along the direction of R will be F cos theta, and the perpendicular distance here will be F sine theta times R. Okay, so let me just try and draw that quickly over here. Let me get the pen just to make that a little bit clearer. Okay, so we have here, right, that will be F cos theta, right, and that its line of action passes through point O, so its moment effect will be 0, right? Or the perpendicular distance between F cos theta and point O is 0. And then we have F sine theta, which will be out in this direction here. Okay, so if you want to put it over here, can, but I tend to not do that because it changes the location of the line of action of the force. So this is our component of F perpendicular to the R direction, right? So that's what we have here, F sine theta times R. So we get the same thing there as we got previously. All right, let me clear all that away. And then since the force is a sliding vector, we know that it can be moved anywhere along its line of action from the principle of transmissibility. So you should have studied this in maths and or physics previously. So we can define the position vector to anywhere along the line of action of the force and still calculate the same moment. And we'll see that in an example. Okay, so cross product, a quick revision. So as I said before, the R cross F is not the same as F cross R. So when you're calculating the moment, you need to make sure you do R cross F, not F cross R, because the commutative law is not valid for cross product. All right, so here, if we did F cross R, we'd get the moment vector going in the wrong sense. Okay. So you need to remember your IJK or your unit vector notation, and you should hopefully remember that if you do I cross J, you get positive K. Okay, whereas if you do J cross I, you get minus K. And I've shown that here, so I listed them all out, all the I cross J, J cross K, etc. And if you do the cross product of vectors along the same line, you get 0. Okay, so I cross I, J cross J, K cross K, all equal 0. Right. Now you can remember which way to go to get whether you get a positive or negative answer by using this circle. So if you go I, J, K, and you go around the circle anti-clockwise, so I cross J gives you positive K, J cross K gives you positive I, K cross I gives you positive J. And if you have a scalar, then you can just put that through like that. All right, scalars are easy. So I've just included in the slide here a couple of pages from the statics textbook by the same author that we have for the textbook for this subject. So the textbook that we have doesn't actually have this page. So when we do cross products, we can do it by finding the determinant. Okay, so again, if you need to, go back and revise your maths modelling from previous semesters for how you determine the determinant. Okay, so you can just do the multiply through like this, or you can use the determinant method. And I've got a couple of examples coming up where firstly I do just multiply everything through, and secondly I use the determinant. Okay, so I've just got here some, so here's just showing in general force in any arbitrary direction, position vector from point O to somewhere along the line of action of that force generates a moment. And we can calculate that moment by finding the determinant. Okay, and expanding this determinant gives this equation, right? So we just need to remember that we've got a negative out the front of the J when we calculate the term out the front of the J unit vector. Okay, so we just do that multiplication. Oops. Well, where are we? Right. So for I, we go AY times BZ minus AZ times BY. Okay, as we've got here, and then we've got a negative sign when we do J. Okay, so firstly, an example. So we've got this post with a lug on the end and a couple of forces. So this is the same problem that was done in the scalar moment example, or the scalar formulation of moments. But this time we'll write the forces and their positions in vector notation, and then we'll determine the moment about point A using the vector cross product. So write the forces and their positions in vector notation. So firstly, we need to define some axes, and you need to show those on your solution, right, so that people reading your solution know what you're talking about and can check your working. Right, so I've defined X positive to the right and Y positive upwards with the origin at point A. To find the vector notation of the force, we need the components in the X and Y directions. So hopefully you know how to do that without me going through all that again. Again, what I will say is note how I always put my components like this. In physics, they often show you when calculating or when drawing components to put the component out here like this. Right? I don't like that because it moves this component of the force off its line of action. Right? So then when you go to look at, well, what's the moment effect of this force? It looks like it's acting out here and you're looking for this distance here, right? Which is not correct. All right, so this is a simple Pythagoras theorem, high school maths, to work out those components. And then we put those into our vector notation. So in the X direction, we have the I unit vector. In the Y direction, we have the J unit vector. And they're both in the positive directions according to our coordinate system that we've specified. Let me get my laser pointer back here. There we go. Okay. And our weight vector here, or the weight of the lug expressed as a vector. So it's just going in the I direction, sorry, the J direction, in the minus J direction. so then we have our position vector for F. So you just define this vector that goes from point A to anywhere on the line of action of the force. So obviously the most convenient point to work that out is this point here where the force is applied, because we've already got these dimensions. So the position vector there, so if you like, stop the video if you're watching this at home, and see if you can write down the position vector for F. All right, hopefully you've done that. And as we can see here, I've now just converted this from millimeters to meters, as you can see by my indication of the units here. So in the X direction, we've got 0.5 meters positive, so 0.5 I, and in the Y direction, it's 0.9 meters in the positive Y direction, so positive J. So that's our position vector for F. Our position vector for the force W. So we need to pick a point anywhere along its line of action. We're not given a position where the force is applied or a dimension here, so let's assume 0.8 meters. But hopefully you can foresee that it doesn't matter what we assume for the Y location. Okay. And you might like to think about why that is as we work through the problem. Okay, so in the X direction, we've got 0.2 meters, so 0.2 I, and in the Y direction, we've assumed 0.8, so 0.8 J. So determine the moment using the vector cross product. MA is the sum of all of the R cross Fs, all of the forces and their position vectors. So R subscript F cross F, so our position vector was 0.5 I plus 0.9 J times, or cross product. It's not really times, it's cross product. The force vector. And as I said, in this case, I'm just going to do the multiplying through to find the answer. So if we just take out our 400 out the front, because that's common. So as we saw before, it's a scalar, it just multiplies through, so it doesn't matter where we put it. So we have 0.5 I times cos 30 I, 0.5 I times cos 30 I, so we've got I cross I here, and then 0.5 I times, so we're just multiplying this one through again, so 0.5 times sine 30 degrees, so that one's coming down here, and we have I cross J comes into here. And then we have 0.9 J multiplied through, so 0.9 times cos 30, so we have J cross I down here, and then 0.9 J times sine 30 J, so J cross J. So if we multiply through, right, so here I cross I will be 0, J cross J will be 0, I cross J is K, and J cross I is minus K. Just put that in there for you, or you can go back and look at the previous slides to help you remember. So doing the multiplication, doing the maths, and putting in K and minus K. So you can see here now that the direction of the vector moment here is in the K direction. All right, so doing the maths, we get minus 211.77 K Newton meters. All right, so if we now do the cross product for the position vector to the weight vector, so we had 0.2 I plus 0.8 J times minus 100 J. All right, if we multiply that through, so 0.2 times 100, 0.2 I times 100 J, so 0.2 times minus 100 is minus 20, I cross J, right? So I cross J, do I put it here? Yeah, I cross J is positive K. and then 0.8 times 0.8j times 100j is j times j, which is 0, right? So as we said before, it wouldn't have mattered what number we put here. It doesn't matter what we assumed for the point of application of this weight force, wouldn't have changed the answer, which also indicates that, right, as we said before, we can make our position, define our position vector anywhere along the line of action of the force, and we'll still calculate the same moment. Okay, so for example, we could have come down here and said that our position vector was just 0.2 I, right? And we would have got the same answer. Okay. So adding those together, we get minus 232 k Newton meters, which is the same answer that we got previously with the scalar method. Note also that the negative sign indicates a clockwise moment. All right, so so we can see that. So this force down here will tend to cause a rotation around this way. Similarly, the weight force will tend to cause a rotation around this way, which is clockwise. Okay, so using the right-hand rule, if you do that into the page, your thumb points into the page, so it's in the negative Z direction. Okay, which also indicates why I said previously that, strictly speaking, if X and Y are defined as positive to the right and positive vertically upwards like this, then you should be taking anti-clockwise as positive. Now, it doesn't matter in 2D problems, but in 3D problems it does. All right, now I'm going to stop, and I'm going to come back with the going through this problem.